The Chemistry of Smog, Unraveling the Mystery. Title: The Chemistry of Smog, Unraveling the Mystery. Introduction. Smog, a notorious phenomenon plaguing urban areas, is a visible haze that hangs over cities and disrupts the natural beauty of landscapes. This pervasive air pollution poses a serious threat not only to human health but also to the environment. Understanding the chemistry behind smog is crucial in unraveling this atmospheric mystery and devising effective strategies to combat it. In this article, we delve into the intricacies of smog formation, its detrimental effects, and the role chemistry plays in this complex process. What is smog? Smog, a portmanteau of smoke and fog, is a mixture of various air pollutants. It occurs when certain gases and particles react in the presence of sunlight and create a toxic haze. Smog is most commonly found in densely populated urban areas with high levels of vehicular traffic and industrial emissions. The major types of smog are photochemical smog and industrial smog, each with distinct chemical compositions and formation processes. Understanding smog formation. To fully grasp the chemistry of smog, we need to analyze the components involved in its formation. The primary contributors to smog are nitrogen oxides, NOx, volatile organic compounds, VOX, and S. Unlike nitrogen oxides, NOx, these compounds, typically formed from the combustion of fossil fuels, are major contributors to smog. Nitrogen dioxide, NO2, is the main component of NOx. Volatile organic compounds, VOX, which include a wide range of carbon-containing compounds, originate from vehicular exhaust, industrial emissions, and chemical solvents. These compounds readily evaporate at typical ambient temperatures. Sunlight, solar radiation initiates the complex chemistry that leads to smog formation. Sunlight provides the energy required for the crucial reactions within the atmosphere. Chemical reactions involved. The chemistry of smog formation involves a series of reactions known as photochemical reactions. These reactions occur primarily in the presence of sunlight and involve the following steps. 1. Formation of nitrogen dioxide. Nitrogen dioxide, NO2, is produced when nitrogen oxides, NOx, react with atmospheric oxygen. This reaction is often catalyzed by sunlight and occurs predominantly in urban areas with increased NOx emissions. 2. Production of ozone. Ozone, O3, a key component of smog, is formed as a result of the reaction between nitrogen dioxide, NO2, and oxygen atoms. This reaction requires sunlight and takes place in the presence of volatile organic compounds, VOX. 3. Creation of peroxyacyl nitrates, PANs. Peroxyacyl nitrates, PANs, form when volatile organic compounds, VOX, react with nitrogen dioxide, NO2. This reaction leads to the accumulation of secondary pollutants with harmful effects on human health and the environment. 4. Photochemical smog formation. The combination of ozone, O3, PANs, and other secondary pollutants leads to the formation of photochemical smog. This smog is characterized by a yellow-brown color and has adverse effects on air quality. Liddy and human health. The detrimental effects of smog. Smog poses a significant threat to both human health and the environment. Prolonged exposure to smog can lead to severe respiratory problems, including asthma, bronchitis, and reduced lung function. It also contributes to the formation of cardiovascular diseases and various allergic reactions. Moreover, smog has detrimental effects on vegetation, aquatic ecosystems, and the overall quality of air in water. The role of chemistry in combating smog. Understanding the chemical processes involved in smog formation is essential for developing targeted strategies to reduce air pollution. Various approaches are being pursued to combat smog, including 1. Emission control. Efforts are being made to reduce the emission of nitrogen oxides, NOx, and volatile organic compounds, VOC, from industrial sources, vehicles, and other combustion processes. Stringent regulations. Improved emission control technologies and the use of alternative fuels are helping to mitigate air pollution. These technologies aim to remove or transform the harmful components into less hazardous forms. 3. Urban design and planning. Urban planners are adopting design and planning strategies that promote public transport systems, pedestrian-friendly environments, and green spaces. These measures help reduce vehicular emissions and improve air quality in cities. 4. Public awareness and education. Raising public awareness about the causes and consequences of smog is crucial in driving individual actions and promoting sustainable development practices. Educating citizens about responsible consumption, reduction of vehicle usage, and the benefits of clean energy can significantly contribute to smog reduction. From the chemical reactions involved to the detrimental effects and the role of chemistry in combating smog, understanding the complexity of this atmospheric phenomenon is crucial. Smog, a visible composed of various air pollutants, is most commonly found in densely populated urban areas with high levels of vehicular traffic and industrial emissions. There are two major types of smog: chemical smog and industrial smog, each with distinct chemical compositions and formation processes. To fully grasp the chemistry behind smog formation, we need to analyze the components involved. The primary contributors to smog are nitrogen oxides, NOx, volatile organic compounds, VOC, and sunil. Nitrogen oxides, typically formed from the combustion of fossil fuels, mainly consist of nitrogen dioxide, NO2. VOC, on the other hand, originate from vehicular exhaust, industrial emissions, and chemical solvents and readily evaporate at typical ambient temperatures. Sunlight plays a crucial role in initiating the complex chemistry that leads to smog formation by providing the energy required for the necessary reactions within the atmosphere. The chemistry of smog formation involves a series of reactions known as photochemical reactions. These reactions primarily occur in the presence of sunlight and include the following steps. First, nitrogen dioxide, NO2, is produced when nitrogen oxides, NOx, react with atmospheric oxygen, often catalyzed by sunlight. Second, ozone, O3, a key component of smog, is formed through the reaction BET. We nitrogen dioxide, NO2, and oxygen atoms, again requiring sunlight and the presence of VOx. The detrimental effects of smog on both human health and the environment cannot be underestimated. Prolonged exposure to smog can lead to severe respiratory problems such as asthma, bronchitis, and reduced lung function. Smog also contributes to the formation of cardiovascular diseases and various allergic reactions. Moreover, it has detrimental effects on vegetation, aquatic ecosystems, and ovae.